Alright, hello everyone. Today we are going to be doing some practice op-amp problems. So op-amp problems a little more complicated than the ones that we saw last video, but the same principles apply. So right now we are trying to find V naught or V outs, and the best way to solve this is with a nodal analysis. So step one, we are going to label the nodes. And let's see the nodes that we've got. So we have node 1 right here, okay? And that we're going to assign it with a voltage of V1 because we don't know what the voltage is there. And then this one we're going to assign it as N2, but as per the op-amp rule, both of these are the same. So we are going to put V1 right here. We have a super loop up here, and it's forcing 8 volts, so we're going to have a super node right here, and we're going to call this bottom one V2, and this will be V2 plus 8. And then of course we have the node with V naught, and we aren't going to be finding a nodal equation for V naught. Okay, so let's go ahead and perform KCL. First at node 1, okay, and we are going to get V1 minus 0 over 4k. I'm just going to leave off the ohms, and I'm just going to put 4k to as a placeholder for 10 to the third, plus V1 minus V naught, because we have this right here, over 10k. And I actually forgot to mention this in last video. And in that video, I did say that the currents in both these branches are approximately 0, okay? But I never actually explicitly showed it in my equations. But really, this is supposed to have a plus 0 because we have a current going this way, and that way. So I just want you guys to be aware of that. All right, and all of this is equal to 0. Let's go ahead and solve it out. I'm going to multiply by 40. And we are left with 14V1 minus 4V0 equals 0. First nodal equation. Second nodal equation comes from this node right here. And we can see that we have a current this way, this way, this way, and this way, and this way. So we're going to have 4 terms. So the first term is going to be V1 minus 4 over 2k, plus the next term is going to be this 2 milliamps coming out, 2 milliamps, plus, and we're going to have this this up to the super node. So we're going to have V1 minus, open parentheses, make sure that you don't miss that, V2 plus 8 over 1k, plus, and we have our last one, which is into the op-amp, which is just 0. We're going to equal that all to 0. I'm going to go ahead and solve this out. And we're going to be left with 3v1 minus 2v2 equals 16. And now we have to solve our supernode. So this supernode is going to have a current going this way, this way, this way, and this way. Okay, and notice how I didn't write a node right here because we know that this is just 0 volts because it's connected to ground. So this supernode is going to have 4 terms in it, and we are going to have V2 plus 8 minus V1 over 1k plus V2 plus 8 minus 0 over 2k, because one of them is going to ground. Now we're going to look at the non-forced portion. it's V2 minus V naught because we are going outwards and it's touching the V naught node over 2K, and we have 2 milliamps going into this node. Okay. Once again, we're going to solve it. We're going to simplify. And we are left with negative 2v1 plus 4v2 minus v naught equals negative 20. And so these are our nodal equations. You're going to plug them into a matrix and your calculator, and you are going to get v1 is equal to 24 volts, v2 is equal to 28 volts, and v naught is equal to 84 volts. And look at that, very nice numbers, and we get an amplified voltage of 84 volts, which is pretty nice. And for our second problem, we are actually going to have a dependent source. So this is a voltage, a current dependent voltage source, right? Because it is dependent on a current. And we are told what that current is, I, okay? Now, my professor taught us to always remove the dependency, okay? So put everything in terms of what you want to find. And what we want to find is a voltage in this case. So step one, before we even write the nodes, we're just going to go ahead and get I out of the way. So write I in terms of voltage. And remember, we're very familiar with this. We have a node right here, and we just want a current. And in nodal analysis, we find the currents going out of a node or into a node. So why can't we just find one of the currents? So we are going to start as if this is a node, and because it is, and we are going to have I is equal to 10 minus V naught, right? Because this is the current that we're normally going to do. Instead of writing this current also, which we can effectively be I2, we don't actually need it. It's redundant, okay? So we can just have 10 minus V naught over 10, right? Because that defines this current going in this branch, okay? So we've removed a dependency already. Now, we can go ahead and plug this I into this right here, but I'm going to go ahead and set up the equations with I in it just so that you can see something, you know. So step 2, label the nodes. Always label the nodes. We have V1 right here, which we don't know, and I'm going to call it node 1, V1 right here. And remember, it's an op amp, so we are going to have the same voltage going in through this way as well, okay? That will be N1, N2 right here. Okay, actually, I'm going to call this N3. You know why? Because we have this labeled as N2 already. And we're going to call this V2, and this V2 plus 3i. Okay, and those are all the nodes that we need. So we're going to write a nodal equation for N1. And that's just going to be V1 minus 10 over 5 plus V1 minus V2 over 4 is equal to 0. I'm going to go ahead and simplify and multiply by 20. And we're left with 9V1 minus 5V2 equals 40, right? And then we will have the supernode next, N2. Now, we're going to go ahead and solve the supernode, and this supernode only has 2 branches, two currents. So we have V2 plus 3i minus V1 over 1 plus V2 minus V1 over 4 is equal to 0. We're going to multiply everything by 4. And notice how we have this dependency still here, and it's a current, right? It's a current dependency. And that makes sense because remember, we're adding up all the currents for KCL. So we are going to have, but since we have I defined in terms of our desired voltage, sorry, my screen seems to be freezing. So we have 12I, and the I, we are just simply going to plug in as 4V2 plus 12. I don't know why it's so laggy, guys. 10 minus V0 over 10 minus 4V1 plus V2 minus V1 is equal to 0. Now we can simplify. I'm going to multiply everything by 10. And we are left with negative 50V1 plus 50V2 minus 12V0 equals negative 120. And feel free to divide it out by 2 if you would like to. It's going in the calculator either way. Now we are going to solve for N3. N3 should also be fairly simple and straightforward. We have current going this way, current going that way, and current going that way. So we have V1 minus V2 plus 3, and I'm already going to put the dependency in there. 10 minus V0 over 10 over 1. Oops, I'm running out of room. Plus V1 minus V0 over 20 equals 0. Well, plus 0 to account for the current that's going through into the op amp, which is 0. And we're going to multiply everything by 20. There we go. And we get 21V1 minus 20V2 plus 5V out equals 60. And if we plug this all in, we get V1 is equal to 10 volts, V2 is equal to 10 volts, and V3 is equal to 10 volts, or V0 is equal to 10 volts. And so our answer is 10 volts. And feel free to check this at the end. And that's it for this video. In next video, we are going to be going over capacitors and inductors and including differential equations into our circuit analysis tools. All right.